Okay, in today's lecture, we're going to talk about states of matter and intermolecular forces. Okay, and intermolecular forces are different than the typical forces we think about in chemistry, like chemical bonding. So before we get into intermolecular versus intramolecular forces, let's start off with the basics of states of matter. And let's think about why certain compounds are liquids at room temperature, like this, are gases at room temperature, or are solids at room temperature. And the fundamental difference between these states of matter is really the strength of the intermolecular forces of attraction compared to the temperature of, that ambient condition. So stronger intermolecular forces will tend to bring molecules closer together, while weaker intermolecular forces will be overcome by slight increases in temperature. Usually we call these two phases of matter, solids and liquids, condensed phases, because here the atoms or molecules are close together. So a lot of times you'll see this, especially in relation to gas phase chemistry, you'll see solids and liquids sort of grouped together and called condensed phases. Again, because here the atoms and molecules are basically touching, whereas gases, of course, they're spread much further apart. Now, what governs at a certain temperature whether something is a solid, liquid, or gas depends on the balance, okay? And the balance we're going to consider here is the intermolecular force, which we'll abbreviate IMF here, versus temperature. This is really what we're interested in. This is the tug of war that determines whether something's going to be a liquid, solid, or gas. So for a given compound like water, which has certain intermolecular forces, of course, as we change the temperature, we might overcome those intermolecular forces and move from solid to liquid to the gas phase. Now, what we want to think about here is that temperature is really a measure of kinetic energy. So when we say increased temperature, what we're really talking about is this motion of the atoms or molecules being increased. And throughout this lecture, and of course other lectures going forward in this course on general chemistry too, it's really important to have this mental picture of what the atoms and molecules are doing. Okay, that's what I really want to concentrate on, because if you can visualize this microscopic behavior, you can then understand the concepts and connect them to our macroscopic observations. And really that's what chemistry is all about, being able to explain nature based on the functioning of these very tiny microscopic or nanoscopic entities, whether it's atoms or molecules. And so while we think of states of matter, which state of matter is a certain substance in, it really relies on the balance between the kinetic energies of the particles and the interparticle energies of interaction. So this should probably be a colon here. It depends on these two things, right? The kinetic energy, this is temperature, and the interparticle energies of attraction, this is what we call the intermolecular forces. And so let's first think about this solid down here, right? These solids, you picture them as being these static things, right? Here's a crystal lattice of all of these atoms in a nice, neat row. And we certainly draw them and tend to think of them as these fixed things. Maybe there's like these metallic bonds between them if they're a metal, right? But they're in this nice sort of cubic structure, and they're not really jostling around very much. We think of it as this static picture, but in actuality, they are moving a little bit, okay? They have a very small kinetic energy, though. Very large attraction between the two, nearest neighbors here in this solid lattice. Of course, even if this atom right here is moving slightly back and forth, what we can do is increase the temperature or add a bunch of energy, and now this atom maybe gets moved out here a little bit further, right? So we've taken this atom, and as we've increased the temperature, we've moved this out to the left. Of course, it's dynamic. It's not sitting out here to the left. It's vibrating back and forth, and it comes back to the right, then it goes back to the left. It's jostling around as we increase the temperature, and all the atoms are going to do that. Eventually, right, you heat this thing up enough, you add enough energy and increase the temperature, Well, now you've melted the thing, and it's not in this certain lattice anymore, but now the picture, instead of a solid, is like this liquid. Things are sort of jostled up, not in a nice, neat, uniform relationship. And so as you increase the temperature, you're adding the kinetic energy to this particle, increasing the molecular motion, the atomic motion. These things jostle around much, much more. And now they sort of roll past one another. And that's the sloshiness that we usually call a liquid. So you can increase the temperature even more. The kinetic energy, overcomes the intermolecular forces here. The reason these things are still, close to each other, even though you've given them enough energy to melt the thing, and the atoms or molecules roll past one another and jostle about, they still stay close, right? That's because of this energy of attraction, intermolecular forces. So they're still close together because, you haven't given it such a boost in energy that you're able to tear the molecules apart from one another, but you've given them enough so that they're sort of, oiled up and roll past one another, and now they're in the liquid phase. So if you keep increasing the energy, well, now you can enter the gas phase. Now you can completely take one of these molecules and liberate it from its neighbors. And now it can go hurtling off into space, right? And so that's how we approach this gas phase picture. Now, exactly what temperature this melting or this vaporization happens at, how much energy do you have to add? Well, it depends on the exact kind of intermolecular force. And that's what we're going to talk about moving forward, the different kinds of intermolecular forces and the different strengths involved that dictate what temperature these phase transitions happen at. Now, I think it's important again to have this molecular level picture. So what I want to show you now are these different molecular pictures here for different states of matter for water. So here we are at 146 Kelvin, best temperature scale, or negative 127 degrees Celsius, second best temperature scale. Really, really cold. But, and this is a really important part, have some appreciation for how chaotic, the molecules look at the molecular level, right? They're not these fixed in space points, right? Each of these little, red and white spheres, these groups of 3 atoms, are a water molecule, but they're still shimmying around quite a bit, right? Even at negative 127 degrees Celsius. So there is still a lot of sort of this rattling in the solid lattice structure. Now, as we heat this up, we're going to, of course, add more of this jostling. So now we're at negative 44 degrees Celsius. Still pretty cold for us humans, but not that cold that things are, motionless at the atomic scale. We keep heating this up, and now we're in the liquid phase. So we can go back and sort of approach this a little bit more slowly, right? Now we're sort of forming these certain areas where things are jostling more or jostling less, and it's not a perfect cube structure anymore. We're sort of getting close to the liquid phase, and now there's certainly pockets of ice-like structure, but now we're entering the liquid phase. Okay, and now here at 6 degrees Celsius, right, 14 degrees Celsius, we're well past that, melting point from the solid water, which we call ice, of course, to the liquid water. And now at 14 degrees Celsius, maybe we'll go up to room temperature here, somewhere around 20. This is liquid water, right? It's certainly flatter and taking the shape of the bottom of the container here, which is characteristic of a liquid. You don't have this nice, neat crystal lattice structure where you see these pockets, right? Like you have in ice. We'll see later on in a future lecture that this is the result of hydrogen bonding and is the reason why ice is less dense than liquid water and floats on top of liquid water. But that's a future lecture. But here in the liquid phase, you can really see how chaotic it is, right? Stuff is jostling all about. Look at this guy down here. He's really going crazy. Things are rotating, things are vibrating back and forth, but everything's pretty much down here in the liquid phase. Now, as I begin to heat it, of course, there's a distribution of energies. Temperature is an average kinetic energy, so as I start to add energy, some of these molecules might get enough energy, even before the boiling point, to get shot off into space. So now we're at 84 degrees Celsius, and now they're really spinning around, right? It's still clearly a liquid, but you'll see now we have a gas molecule of water up here, okay? And so some of these are getting enough energy to completely leave their liquid friends because you've given them enough energy to overcome that intermolecular force, which is hydrogen bonding. Okay, eventually, of course, we add enough temperature, and it takes some time for the animation to play out, but eventually these things have enough energy, they're all spreading out, they're going into the gas phase, and you approach something like this. Okay, so again, this is the sort of picture I want you to have in mind when you think about these various states. A solid, yes, there's this nice like periodic structure, but there's still an awful lot, more than you would think, motion in here at the microscopic level. Liquid, there's still neighbors that are really close to us if we're a water molecule, and those neighbors have a lot of energy, so do we. We're dancing about, we're bumping into other things. And the gas is when we're more or less colliding off other water molecules. We might interact a little bit with another water molecule, but we pretty quickly then fly back apart as well. So again, it's all about this balance between what temperature you're at and the strength of the interparticle energies. Here we have an interparticle energy like intermolecular forces, and that's like hydrogen bonding, I should say, is our intermolecular force here. And that's a pretty strong force. So it actually takes a lot of energy to get this ice into the liquid phase or to get that liquid into the gas phase. So intermolecular forces is what we're concentrating on in this lecture and the next couple lectures. And just to more rigorously define it, these are attraction between molecules that aren't quite as strong as intramolecular attractions. So if we think about the water molecule we were just looking at, here's my oxygen, here's my hydrogen, here's my hydrogen. And these right here, you remember our Lewis structures, those are our chemical bonds. And these chemical bonds right here, that's what we call an intramolecular force. Okay, this is inter, we'll get to that in a second, but this is intramolecular. Molecular meaning molecule, intra meaning within. So if you think of something like intramural, that is a sport within a single university, right? Intramural sports is within a university, different sports teams playing each other. Okay, that's what a chemical bond is. Okay, within this molecule, it is the forces holding the atoms together in that given molecule. Now, if we have another water molecule with its intramolecular forces, its chemical bonds, what we'll see going forward is that, well, one hydrogen can be attracted to a nearby oxygen on a separate water molecule. And now this here is intermolecular. And the exact kind of intermolecular force is a hydrogen bond, which is a poor name because a bond, it's not really a bond. We just call it a hydrogen bond, but it's not like a chemical bond. So this is a special kind of intermolecular force. So these are the two separate forces you want to keep in mind. Okay, the intramolecular chemical bonds are much, much stronger, but the intermolecular bonds, the intermolecular forces aren't chemical bonds, but they're really responsible for things like boiling points and melting points, viscosity, surface tension, capillary action, okay, sublimation points, these types of properties. It's not actually the chemical bonds that matter for boiling points or melting points or viscosity. It's these intermolecular forces. So the forces that are holding some molecules of a substance to other molecules of the substance. So that's what we're showing here. You can see the rattling around of the water molecules, even at this low negative 127 degrees Celsius. Why they aren't breaking free? It's because of this hydrogen bonding intermolecular force that's holding one water near another water. So maybe we'll pause here and think about the answer to this question before we proceed. So maybe take 30 seconds and try to answer this before we discuss this question and move on. All right, time's up. So when water boils, what are the bubbles composed of? We can first think about, before we answer the question, what does it mean to boil? This is a change of state, right? Boiling point is one of these things we just said is related to these intermolecular forces. So the picture we want to have here is that when we boil something or when we melt something, it's a phase change. We're not changing the chemical composition. All we're changing, right, is overcoming this physical force, not a chemical bond, but a physical property is what we're concerned with here. And these are governed by these intermolecular forces. So when water boils, all we're doing is overcoming this intermolecular force. It's still going to be a water molecule. We haven't broken any chemical bonds here. We're just overcoming those intermolecular forces. So as we're adding temperature, as we're adding heat, I should say, and the temperature gets to 100 degrees Celsius and the water boils, those bubbles that we're seeing are just gas phase water. So the answer here should be D. We're still seeing water. It's not oxygen gas, it's not hydrogen gas, it's not both of them, it's not other impurities. We haven't done any chemistry here. This is just a physical change. And so it's still water that we're seeing. And of course, as those bubbles reach the surface and they get released, we see this steam and this vapor that, again, is still water molecules. So we're not doing any chemistry there per se, just a physical change. And so it's these kinds of processes that we're going to concentrate on in this and the future couple of lectures, because those are related to intermolecular forces. Again, things like boiling point, surface tension, viscosity, capillary action, melting points, etc. And again, for water, this happens sure at 100 degrees Celsius, but water actually has fairly strong intermolecular forces. These are the different types of intermolecular forces, weakest to strongest: dispersion, dipole-dipole, hydrogen bonding, which we sort of hinted at today, and ion-dipole forces. And so as you go from top to bottom, these get stronger. So hydrogen bonding is pretty strong as a force, and that's why you have to get to 100 degrees Celsius before water boils. Now, if you add a different substance that only has, say, this weak force like dispersion, well, you probably don't need the temperature to get as high before it boils, and that's what we'll see in future lectures. Note that the first two here sort of get grouped together sometimes, and we call these van der Waals forces or van der Waals forces. And these are pretty weak, contrasted with hydrogen bonding and ion dipole forces. Right? These are all examples of intermolecular forces. None of these are a strict chemical bond, which would be an intramolecular force, but are just intermolecular forces. So that'll do it for this first introductory video on intermolecular forces. Next time we'll actually get into visualizing and describing dispersion forces and dipole-dipole forces. And we'll follow that up with another lecture on hydrogen bonding and ion dipole forces. That's it for this video. See you next time.